Hello everyone, welcome to my channel. In this video, I'll be looking at Introduction to Linear Algebra. If you're new to this channel, don't forget to subscribe, like these videos, provide feedback. We truly value your feedback. So we start the Introduction to Linear Algebra, and we're going to start by defining what a matrix is. So we define a matrix as a rectangular array of numbers. We define a matrix as it is a rectangular array of numbers. We call these numbers elements of a matrix. These numbers, let me just clean up a little bit here. These numbers are known as elements of a matrix. These numbers are known as elements of a matrix. So we define a matrix as a rectangular array of numbers. These numbers are known as elements of a matrix. I want to start by looking at examples. After our definition, which is this one here that I've just given, let's look at examples of matrices and their dimensions. So examples of matrices and their dimensions. Examples of matrices and their dimensions. Right. Let's look at number one. I want us to look at this example of a matrix. Sometimes we use round brackets or square brackets. So I'm going to have 1, 2 here, and then 3, 4, like that. This one here is known as a 2 by 2 matrix because it has 2 rows and 2 columns. So 2 by 2 matrix. The first 2 represents the number of rows, and the second number here represents the number of columns. So this is a 2 by 2 matrix. Let me give another example. Example number 2. What if you have 2 and then 0 and then 5? There is only one row, but there are 3 columns. So this is actually a 1 by 3 matrix. It has one column, one row, and then 3 columns. Remember, number of rows, the first value or the first number is the number of rows. In this case, we have one row, okay? And then that one represents number of columns. We have one row, but I'm saying rows because that's the position where you place the number of rows and then you place the number of columns there. But we have one row and 3 columns, one row and 3 columns. So this is a 1 by 3 matrix. Let me give another example, number 3. And number 3, I just want to look at a simple one. Suppose, and I told you that sometimes we use square brackets. What if I have 1 and minus 2, like this? This, we have 2 rows and 1 column. So this is a 2 by 1 matrix because it has 2 rows and 1 column. You can see 2 rows and 1 column. Right. Let me give you example number 4. It takes me to page 2. Example number 4. Example number 4. What if you have the following? Let's say you have minus 1, 2, 3, and then you have 0, 1, 5, and then you have minus 3, let's say 4, and let's say 1. The question is, how many rows do we have here? We have 1, 2, 3 rows. How many columns do we have? We have 1, 2, 3 columns. So this is a 3 by 3 matrix. We have 3 rows and 3 columns. Right. Sufficient examples. I've given you 4 examples. But I want to now move on to what we call basic operations, basic matrix operations, or elementary matrix operations. That will be my next step. So elementary matrix operations. I'll be looking at number 1, addition. Yes, matrices can be added. Remember, 1 is a matrix, many are matrices. So matrices can be added, but there's a rule there. So matrices can only be added if they have the same dimensions. So what I mean by dimensions are these ones here that we write there. For example, this is the 3 by 3 matrix. So these are the dimensions of this matrix. So I'm saying here matrices can only be added if they have the same dimensions. So let me just give examples of matrices that can be added. Suppose we look at the following here. Suppose we look at number 1. I have 1, 2, 3 minus 1. And I'm saying this matrix here is equal to A. So A equals this. Let's have B equals, we have another one, let's say 2 minus 1, and then let's say 4, and then 5. Can we add, can we evaluate A plus B? The answer is yes, we can, because A is a 2 by 2 matrix, 2 rows and 2 columns. B is also a 2 by 2 matrix. And because these matrices have the same dimensions, I can add them. So A plus B is just going to be, watch this, it's just going to be, I'm going to take that term or that element, add to that element. An element in first position must be added. First position, remember, first position in row 1 and column 1 must be added to first position in row 1 and column 1. So this is 1 plus 2. The second position in column 1, but first position in row 2. So this is row 2. Remember, row 1, row 2, column 1, column 2. So this 2 here is in first position in column 1, but is in the second position in column 1, because this is first position, second position in column 1. So 2 is in the second position in column 1, but it is in the first position in row 2. Notice row 1, row 2. So we're adding that to that. Basically, you can see this must be added to that in simple terms. 3 plus 4, and then 2 plus 1 minus 1, and then minus 1 plus 5. So let me just continue then. 2 plus minus 1, and then we continue on the other side. We're going to say 3 plus 4, and then down here we're going to say minus 1 plus 5. And then we simplify this. It gives us 3, 1, because 2 plus minus 1 is 1. And then we have 7 there, and then we have 4, because minus 1 plus 5 is 4. So this is the solution. Now notice something. When we add a 2 by 2 matrix to a 2 by 2 matrix, we obtain a 2 by 2 matrix. So there is a story there. Basically, we are saying when we're adding n by n, let's say I'm saying here, when we add n by n matrix, we're adding this to another n by n matrix. What do we produce? We produce an n by, sometimes we use this sign for by. So n by n plus n by n will give us n by n. This is the same as n by n. Right. So that's basically what we're saying. Let's look at another example. Remember the condition? Matrices can only be added if they have the same what? Same dimensions. Let's look at example number 2 on addition of matrices, and I'm going to move to subtraction of matrices as soon as I'm done with addition of matrices. Let's look at example number 2. Now I want to add example number 2, simple example. Let's say we are talking about 2 minus 1, 0, 1, 5, 3. This is a 2 by 3, 2 rows and 3 columns. We're adding these two. Let's have another 2 by 3 because that's the only way we can add matrices. Let's say we have 1 and then 3. Let's say we have 1 and then minus 1. Let's say we have 3 and then 2, like this. 2 by 3 matrix, also 2 by 3 matrix. Can we add them? Yes, we can. So we're going to take first position, first position. So we're going to say 2 plus 1. And then down here, this minus 1 will be added to 3. So minus 1 plus 3. And then we're coming to the second column. We're going to say 0 plus 1. 0 plus 1. And then we're going to say 1 plus minus 1. 1 plus minus 1. And then finally 5 plus 3. And then we're going to say 2 plus 3 plus 2. 3 plus 2. Simplifying this, it gives us 3, 2. Remember, minus 1 plus 3 is 2. And then you have 1 there. And then here you have 0. And then you have 8. And then you have 5. So this is our final solution. Again, 2 by 3 matrix, 2 by 3 added to a 2 by 3 produces a 2 by 3 matrix. Let's talk about subtraction. I'm moving on. Let's talk about subtraction, elementary matrix operations. Remember, this is where we're at. And I've talked about addition. I want to talk about subtraction. Subtraction, number 2, elementary matrix operation 1 was addition. Now we're looking at number 2 here, subtraction. And subtraction. Now we are also saying matrices can only be subtracted if they have the same dimensions. Otherwise, you cannot subtract matrices if they have different dimensions. Let's give examples here, just a few, maybe 2 examples. Given, let's say, B as a matrix. We're talking about subtraction of matrices here. So let me just say we have 1, 2, minus 5, and then 3, 4, minus 2. That is a 3 by 2 matrix. And we're also given C is equal to, let's say we have 1, 1, 1, and then 2, 2, 2, just for argument's sake. Is it possible for us to have determine here, determine B minus C? Sorry, B minus C. My hand is messing up here. Determine B minus C. Let me just move this all together to the far side. Determine B minus C. Can we obtain this? Yes. Can we determine it? I want to show you how we go about it. Very simple stuff we're looking at here. Remember how teaching and learning is done. We start from concrete to abstract. So we are told that our B, let me capture the matrices again, equals 1, 2, and then minus 5. Then we have 3, 4, and then minus 2. And then we're told C is equal to, we have 1, 1, 1, and then 2, 2, 2. We are required to work out B minus C. Therefore, B minus C will be equal to, watch this, 1, 2, minus 5, and then 3, 4, minus 2, and we're going to say this minus 1, 1, 1, and then 2, 2, 2. What are we saying? We're basically saying that this number minus that number. So first position minus first position. So that's going to be 1 minus 1. And then in the second position there, I'm going to say 3 minus 2. Then I'm coming back here, it will be 2 minus 1. Or if you continue, it will be minus 5 minus 1. And then down here, it will be the central part, it will be 4 minus 2. 4 minus 2. And then finally, we're going to say minus 2 minus 2. Minus 2 minus 2. Let's simplify this. This is going to be 0, 1, minus 6. And then we have 1, 2, minus 4. Again, subtracting 3 by 2 matrices will produce a 3 by 2 matrix. Don't forget that. All right, maybe one more example on subtraction of matrices, and then we'll move on to multiplication of matrices. One more example. I'm just going to give example. This was example 1. Let's call it, or yeah, let's call it example 1. And I want to give example number 2 here. Number 2, determine, let's say, m minus n if m is equal to, let's say, simple matrix 3 minus 2, 5. That's m. And then n, I'm going to have, let's say, minus 1, minus 2, and then 3. So basically, we're saying m minus n will be equal to this matrix minus that. Remember, this is a 1 by 3 matrix, and that's also a 1 by 3 matrix. So it's going to be 3 minus 2, 5, and then we're saying minus, we're here, minus 1, minus 2, 3. This will give us, if I go to page number 5, this will give us the following information. Page 5. Let me move this one down. Right. So this one is going to give us our solution that looks like this. Here, 3 minus minus 1. Remember, 3 minus minus 1. And then in the second position, it's going to be minus 2 minus minus 2. Minus 2 minus minus 2. And then finally, it will be 5 minus 3. 5 minus 3, like so. What is our final solution? It's going to be 4. Remember, 3 minus minus 1 is 3 plus 1, which is 4. And here, minus 2 plus 2 is 0. And then finally, 5 minus 3, the answer is 2. So we, again, are ending up with a 1 by 3 matrix. Right. Subtraction of matrices done. I want to move to multiplication of matrices now. So we are basically saying on multiplication of matrices, basic operation number 3, multiplication of matrices. There's a rule again. Remember, on addition and subtraction, same rule. 2 matrices can only be subtracted if they have the same dimensions. 2 matrices can only be added if they have the same dimensions. But multiplication, the rule is slightly different from the that of subtraction and addition. So we are saying here, 2 matrices, this is a rule now, 2 matrices can only be multiplied if the number of columns of the matrix on the left, matrix on the left is equal to the number of rows of the matrix on the right. So basically, I'm saying 2 matrices can only be multiplied if the number of columns of the first matrix or matrix on the left is equal to the number of rows of the matrix on the right. So basically, what are we saying? We're saying we're saying, for example, that if you have an m by n matrix, and this is getting multiplied by an n by let's say T matrix, the number of columns of the matrix on the left, that's a matrix on the left, and that's matrix on the right. The number of columns, remember we have rows and columns. So m by n, it means we have m rows and n columns. Multiplying by another matrix which has n rows and T columns. If the number of columns of the matrix on the left is equal to the number of rows of matrix on the right. In this case, whenever these two numbers are the same, then these matrices can be multiplied, and the resulting matrix must be an m by T matrix. Take note of that, and I'm going to give examples to just prove that. So it's getting a little bit more interesting now. We're moving slowly but surely into abstract stuff. Now let's look at examples here. Examples on matrix multiplication. I'm gonna look at the first one here. Guiding principle. If you have a 2 by 1 matrix, let me use the word by so we don't have to confuse it with the multiplication sign. If we have a 2 by 1 matrix multiplying by a 1 by 3 matrix, because these numbers are the same, the resulting matrix is going to be a 2 by, I'm used to using a multiplication sign for by 2 by 3 matrix. Let's just check if this is true. I think there is somewhere I used TPEX to try and remove some information, and have to come back and fix it on some page, but let me just carry on for now. We'll see. So this one here is 1 by we're saying 1 by a 2 by 1 matrix, 2 by 1 matrix multiplied by a 1 by 3 matrix. The resulting matrix will be a 2 by 3 matrix. Let's give an example. 2 by 1. So we have, watch this, we're multiplying this by 1, 2, 3. This is our example here. 2 by 1 multiplied by 1 by 3. And I'm saying that we are supposed to produce a 3 by 2 by 3 matrix. So basically, how does multiplication go of matrices? This is what we're going to do. Watch this. I'm going to take the 2, multiply by 1, that's 2. 2 multiplied by 2, that's 4. 2 multiplied by 3, that's 6. And then I'm taking 3. 3 multiplied by 1, and that's 3. 3 multiplied by 2, that's 6. 3 multiplied by 3, that's 9. So this is our resulting matrix of multiplying a 2 by 1 by 1 by 3. So you can see here we have a 2 by 3 matrix. This is correct. Let's give an example, another example. Number 2, again, I'm going to start by a guiding principle there. So suppose we have a 2 by, I'm really used to the multiplication sign for by, right? I'm coming back. So 2 by 3 matrix, 2 by 3 matrix. I'm multiplying this by 3 by 3 matrix. Now, these numbers are the same. We're expecting to produce a 2 by 3 matrix. 2 by 3 matrix. That's the resulting matrix I'm expected to produce. Let me just give an example here. E.g., suppose you have 1, 2, and then 3, 4, and then you have 5 minus 1. We're multiplying this by, remember, 3 by 3. So we have minus 1, 2, minus 1, and then we have 0, 2, 1, and then you have 1, minus 1, and finally 3. So this is a 2 by 3 matrix, multiplying it with a 3 by 3 matrix, and I'm saying we're supposed to produce a 2 by 3 matrix. So this is by. Let's look at how this is done. Moving on to page number 7 here. Hopefully I'm moving at a pace that everyone is able to follow what I'm doing. Yeah, so here we go. Page number 7. I just want to make sure that this is put in the right position here. Right, page number 7. I'm basically saying, so now you can see that. Let me move it down. Right, so now I'm saying what we need to do here in order to answer that question. We're going to take, watch this, we're going to take 2 multiply by -1, and then we are going to add 3 times 0, and we're going to add 5 times 1. So basically, first row, first column, multiply and add. So 1 times -1 plus 3 times 0 plus 5 times 1. So basically we are saying, and we're producing a 2 by 3. So let me just say this is equal to, we're saying 1 times, so let me just write it, 1 times -1, and then plus, what else, 3 times 0, 0, plus, then we have 5 times 1, 5 times 1. I'm just going to leave it as 5. Or let me just do this. Right. So you understand what's going on now. So in that position, I'm going to say 1 times 2 is 2, plus 3 times 2 is 6, and plus 2 8. So let me just write 2. 1 times 2 is 2, 3 times 2 is 6, I'm adding, and then plus 5 times -1 is -5. I'm done in that space. I'm moving to the last position now. 1 times -1 is -1. I'm going to say plus. 3 times 1 is 3. And then 5 times 3 is 15. I'm adding, remember. Now I'm going to do the same. Down here, I'm done with that that row. Now I'm coming to the second row. I'm going to do the same. This by that I add, this by that I add, this by that I add. So it's going to be 2 times -1 is -2 plus 4 times 0 is 0 plus -1 times 1 is -1. I'm done with that position. Now I'm moving on to the second place. What am I going to say? 2 times 2 is 4 plus 4 times 2 is 8 plus -1 times -1 is 1. And then I'm on the last space there. It's going to be 2 times -1 is -2 plus 4 times 1 is 4 plus -1 times 3 is -3. And then all I have to do is simplify this. So that will be -1 plus 0 is -1 plus 5, that's 4. And then let me repeat that, -1 and then plus 5, that's 4. And then here we have, that's 8 minus 5, that's 3. And that's 2 plus 15, that's 17. Coming down here, -1 minus 2, that's -3. And this is 12, 13. And finally, that's 2 plus 3, and that's 5. What kind of matrix is this? It's a 2 by 3. Exactly according to what we said there at the beginning, what we said here. So in general, we are basically saying from application of matrices, we are saying in general, let me move this one up. We're saying in general, if you have M by N matrix, let me use that multiplication there. We're multiplying this. I'm going to use a dot for multiplication this time. Multiplying it by N by K, or N by, let's say, W matrix. The resulting matrix is going to be M by W. M by W matrix. This is generalization. So when you're multiplying, this works because these numbers are the same. If you have, you just take advantage of this. If you have A by B multiplied by K by, by K here, or I can use the same letters, no, but I just want to use a different one. K by C, for example. There is no way you can multiply these matrices because they have different numbers of, the number of columns of the first matrix on the left is not equal to the number of rows of matrix on the right. So this multiplication is impossible. Or you can also say A by B multiplied by A by B. This is also not possible because these numbers are not the same. So please take note of this simple principle here that we're using for multiplication of matrices. All right, now I'm done with subtraction, addition, and multiplication. I want to now look at what we call determinants. That takes me to page number, this was page number 7 if I'm not mistaken. Yeah, the last page was page number 7. Let me just check quickly here. Yeah, page number 7. Want to move quickly to 30 minutes already. I want to move quickly to what we call determinants. Determinants. So a determinant of a matrix, determinants only work for square matrices. So what are square matrices? These are matrices whose number of columns equals number of rows. For example, 2 by 2 would be the best one to deal with it, or 1 by 1, or even 3 by 3, 4 by 4. Usually 1 by 1 doesn't work because it's just one number. By definition of the determinant, you will see later that 1 by 1 doesn't work very well. But for a 2 by 2 matrix, yes. 3 by 3, yes. 4 by 4, yes, and so on. So let's start with only for square matrices. So e.g. matrices of the form n by n, yeah, square matrices. Those numbers must be the same. Now there's a reason why we are learning the concept of determinants. So let's look at the definition then. Definition for a 2 by 2 matrix. If you are told that A is equal to, watch this, if you're told that A equals A, B, C, D, if this is what you have, the determinant, which we write in short as det A, also written as this, so to speak, absolute value, if you're talking about differential calculus, but in this case, these two vertical lines mean the following. They mean the product of elements on the right diagonal minus the product of elements on the left diagonal. So this is exactly equal to AD minus BC. Please take note of that. The product on the right diagonal minus product on the left diagonal. That's your right diagonal and that's your left diagonal. Right, so let's look at examples. Examples, just gonna give two. Suppose you have been given A is equal to, let's say you have 1, 3, let's say 2, and what can we say, 9. You're required to work out the determinant of this. I'm just gonna put up example number 2. So let's call this A. So the question here is determine det A, in other words, determinant of A. Number B, suppose you have been given B is equal to, and I want to repeat this story, but using, here I use square brackets and I'm going to use round brackets now. Let's say minus 1 and 3, and let's say 2 and minus 1, like this. And the question says determine, instead of det, they are going to say this. We know it's the same story. And I just want to put up number C here. Suppose you're told C is equal to, and then they tell you that we have x plus 1, and then we have 2 here, and then 3 there, and maybe another x there. And then they say determine det C. How do you deal with this? Remember, now we are beginning to look at something that is a little bit more complex. This is supposed to be page, we've done page 8, I think. Okay, let me not number this because it's gonna waste my time. I think we numbered number 7, so let me just leave it the way it is. Right, so how do we handle this? We're required to determine the determinant of this. Remember the definition, product of right diagonal minus product of left diagonal. So this times that minus this times that. We do the same here and here. And I have example number 2. I think then we'll stop on this one. I'll come back with Cramer's rule to show you why we're having to explain how to determine the determinant of a square matrix is because we want to apply that in solving of simultaneous equations or systems of equations. Right, so let's look at the solution then. Our answers will be as follows. We are talking about example number 1a. We are told a is equal to 1, 3, and then 2, 9. So we're going to say, therefore, det of a is going to be equal to 1 times 9, then minus 3 times 2. This is 9 minus 6, and the answer is 3. Let's look at number, so this is A. Let's look at number B quickly. Number B, we're told B is equal to minus 1, 3, 2 minus 1, and we're required to work out this one here. Again, it's determinant. So it's minus 1, right diagonal, times minus 1, then minus left times, so right diagonal, product of elements on the right diagonal minus product of elements on the left diagonal. So this is 1, if you like, minus, and that's 6. And the final solution is minus 5. Let's look at number C, the last one, on example 1. C, we are told C equals x plus 1, and then we have 2, and then 3, and then x. Now, how do you deal with this? Well, the same procedure, and they're asking us to work out det. So, therefore, determinant of C is equal to right diagonal x times x plus 1 minus 2 times 3. This is x squared, and then you have plus x minus 6, and that's our final solution right there of the determinant. Right now, you see what we're dealing with now. So I'm gonna move on finally to example number 2. That will be the end in this video. Now let's look at example number 2. So example number 2, we are told, I think you can see what I'm writing. Yeah, you can. So example number 2, we are told to solve for x. Now we have matrix equations. A, we are told this is 3 minus x, and then we have 2, and then we have here x 2, and we're told this is equal to minus 2. Number B, we are told that A is equal to 0, where A is equal to, watch this, x plus 1, 2, and then we have 3, and then we have x. So we're supposed to solve the equation. Now, our solution will be as follows. Answer. Let's start with A. So remember, the vertical lines represent determinant. So we're simply going to say 3 minus x, 2, x, 2. We're told this equals minus 2. Right diagonal, this implies 2 times 3 minus x minus left diagonal 2x, and the answer is minus 2. Expand this up. So this is 6 minus 2x. Minus 2x equals minus 2. Minus 4x equals minus 8, if you like. This is minus 4x. And take 6 to the other side, or subtract 6 from both sides. You're going to get minus 2 minus 6 is minus 8. Divide by minus 4 both sides, x equals 2. There is your solution there. The question said solve for x, and that's our solution. Let's look at number B. The last one in this one, number B, number 2b. Remember, number 2b is this one. We are told that A equals 0. In other words, determinant of A is 0, where A is this matrix here. So we're going to say in our solution, so A is equal to x plus 1, 2, and then 3, and then x. Then we're going to say, therefore, that determinant of A is going to be equal to, remember, right diagonal, x times x plus 1, and then minus 2 times 3. What are they saying? They are saying the determinant is equal to 0 there. So we're going to equate this to 0. Solving this equation, we have x squared plus x minus 6 equals 0. Factorizing this, if you have watched my previous videos, I've explained How you factorize this is basically x plus 3 and then x minus 2 equals 0. Therefore, either x plus 3 equals 0 or x minus 2 equals 0. This one gives us x equals minus 3 or x equals 2. Therefore, x equals minus 3 or 2. These are the two values of x that satisfy this equation here. Determinant of a equals 0 if a equals this matrix here. Right, I'm going to stop here. I'm coming back with more on linear algebra because we're just starting linear algebra here. And I want to talk about Cramer's rule, application basically of determinants. And then I will also explain how you work out the determinant of a 3x3 matrix, which can be quite involving. Yeah, but with practice, these things are easy. All right, see you next time.